I'm Zoltán Juhász from Veszprém, and I will talk about a plasma simulation project, which is done in collaboration with the Wigner Research Institute, namely with Peter Hartmann and Zoltán Donko. And I will have one slide about the physics, and then I will move on to CUDA programming and the performance implications of this simulation. I will try to speak slowly because the reverb is really disturbing, so if I speed up, wave your hands so I will slow down again, or if you don't understand me. So we want to simulate plasma. Why do we want this? Because this is important and also fun, and that's about the physics, right? So, but really it is important. There are many industrial applications of this low pressure plasma simulation, and actually the real use of plasma. One of the most important one is the semiconductor manufacturing process, where they use it for etching the silicon. So some of the things can be done in physical experiments, and some of the things we need to simulate. So that's okay, and this thing should be moving. I don't know why it's not doing anything, but basically, if we drive this plasma, which is basically a neon tube with an alternative voltage, we will have a spatial and temporal distribution of the energy, or the particles inside the tube. So this is what we want to simulate, and physicists can discover interesting things after the simulation has got a result. So we are interested in the numerical simulation of this, and the normal method is the particle in cell simulation, which is an n-body simulation, but we are not calculating direct interactions between the particles. That would be an n-square complexity algorithm, which we don't like. Instead, we use this particle-based approach, where we assume that particles are distributed over a grid, and in each grid, we will treat the particles separately, and we will place charges onto the corners of the grid, and from the charge deposition, we can calculate the potential distribution and then the electric field, and eventually, the electric field will move the particles based on their charge. So that's the basic idea. In a normal case, when we don't have collisions, everything's rather simple. We just have to calculate the fields and move the particles, and we start it all over again. The first problem is we have many particles most of the time. We can have 100,000 to 10 or 50 million particles. But the real problem is when the collision comes in. So when electrons and ions will hit each other and something will happen. In the simple case, they will just change their trajectory, position, but in more complicated cases, we can have secondary emissions and even chemical reactions. So the problem is it's a long-running process. The execution time can vary from days to months. In extreme cases, it can run for 6 months on a sequential CPU core. So obviously, we want to speed this up because it's just too much waiting. So we started this project about 2 years ago, and we started with an in-house 1D simulation program, and we had rather low expectations. We wanted to use the GPU to speed up the process at least 10 times higher. So that was the initial goal. And just before I go into the details, that's the outline of a typical Monte Carlo peak or particle in cell simulation. Let's start with electron movements, and we check the boundaries, whether the electrons leave the space or not, or bounce back. Then we do collisions with other particles, and we calculate the density, repeat the same thing for ions, and eventually we solve the grid for the potentials, calculate the field, and we start again. And if you look at these two loops, we have an inner loop for one period of this alternative voltage that we use for driving the plasma, and we have a simulation cycle that we need to reach a steady state equilibrium state. So it runs quite a while. In the initial CPU implementation, this loop, the internal part was roughly 4 seconds. So the outer loop, let's say with 1,000 cycles, ended up with 4,000 or more seconds. So it's about 1.5 hours. And this is the distribution of time for these different steps. And you can see that movement, collision, and density calculations are quite expensive. The field solver, the Poisson solver, is actually negligible, and the boundary checks as well. So we wanted to concentrate first on the density, collision, and the movement. So we got the first implementation, and this is, I mentioned already, I talked about this 2 years ago and 1 year ago. So with the first implementation, which is a 1D simulation on the GPU, we achieved roughly 15 speed up, which was better than we expected. And Peter also developed at the same time a 2D implementation, which was staggeringly fast. We got 100 speed up or 100 times faster than the original program. And that was basically the first of its kind, because 2D collisional plasma simulation is very difficult and very rare. So not many people do it in the world because it takes ages to run it. So this was a big result. So we were very happy. We got good results, but there are 2 questions. The first, is speed up really a good measure? And the other, can we get even better speed ups? So this is what I will talk about. So why speed up is a problem? Because we compare it to a sequential CPU implementation. If you have a really lousy, bad CPU and bad implementation, you get wonderful speed up results. So it's a very unreliable measure. So we want to do something better. So the most objective measure of performance is if we compare our program to the peak performance of the GPU card. So we have to find out how much we can achieve from what the GPU can offer. And one model of this performance is the roofline performance model, which might look a little bit difficult to understand because there are too many formula here, but it's relatively easy. We draw 2 lines. One is the peak computational performance, which is easy. You get it from the catalog, or you can estimate it like that. And the other one is the memory bandwidth multiplied with something we call the operational intensity, which is the ratio of flops to bytes. Okay? And just accept that we get something like this. If we plot the operational intensity and achieved performance on this graph, we can figure out whether our program is compute bound or memory bound, because that's quite an important issue. I will show examples so you will understand in a minute. So the more closer we get to these 2 lines, the better the performance is, the more we get to the peak performance. If not, then we have to think about how to optimize it. So this is the outline of the first GPU implementation we did, and you can see a one-to-one match of the original simulation steps into a GPU CUDA kernel, except the last step, which was a traditional CPU implementation of a 3-diagonal Poisson solver. We didn't want to change that at that time because the time was really not that much, and we were more interested in getting the others right because they were the performance critical factors. So this is the roofline representation of these kernels. This is the operational intensity of the kernel. So if we calculate how many flops we need, or arithmetic operations, in the kernel and how many bytes we read and write, in the kernel, we can calculate this ratio. So in the density calculation, we have roughly 3. In the movement, about 1, and collision varies from 0.6 to 2 point something. And the bad news is that this line is the start of the compute bound performance region. So anything on the, this is a GTX Titan XP machine. So anything below the 16 or, well, it's more 20 actually, 20 flops per byte will be memory bound, which means basically you cannot ever achieve the peak performance of your card. You will be limited by the memory bandwidth. So can we improve on this or not? So this is what we are facing with. We have many kernels. They are relatively small, but slow as well. Small, low arithmetic intensity, and memory bound. And since we have small kernels and we have many, many, many loops, the kernel launch overhead can be significant. So that's another problem. We have tiny kernels, but very many. And we still have a CPU side execution for part of the loop, which means data transfer back and forth in the system. Okay, so a couple of trivial optimization steps. The first, we want to do everything in floats and not in doubles, if possible. If you use GeForce cards, the ratio is 1 to 32 in favor of floats. So if you use doubles, you will get 32nd, well, how do you say that? So 1 over 32, I don't know, 30 seconds of the performance, I don't know, it sounds strange. So anyway, very little performance, that's the point. One other problem is memory access. If you don't have contiguous memory values that you want to fetch in your threads within a warp, then you will slow down the application. So let's just move on to the more interesting things. So when we started the optimization, we also had another problem that we were aiming at a moving target. NVIDIA is so fast in releasing new and new generations of hardware that are all sort of different from the previous generation, that by the time we optimized something for one architecture, the new one arrived and it worked differently. So it's quite a difficult task and sometimes a bit annoying that you think you got something right and in the next generation it's not that optimal. So this is the one we are using. I would like to highlight just 3 numbers. One is that we have over 3,000 cores, over 10 teraflops performance, and over 60,000 resident cells, threads on the machine. So if we run 60,000 threads, you will never have any context switching. So they will be in registers, which is very important from the performance point of view. Okay, so now we'll come back to the first optimization step, which is the particle movement part. So this is the grid. This is our particle, and we have a field, and we have to find out how much force basically we get from the field in this particular position. And the real problem here is this line, because the particle is somewhere and we have to figure out in which cell it will be positioned, but we don't know it in advance. So this is an indirect addressing into the grid or into the field array. And this is something that GPUs just don't like, because you want regular addressing scheme and ideally a one-stride access. So each thread is reading the next address, and this is not very good. By the way, this is a big problem for CPU optimization as well, because this introduces false sharing, and the current solution is that people sort the particles so they will be one after the other in position. So if you read one grid all the particles will be in the same place. But GPU is a different kind of animal. We don't partition the grid and assign it to threads. We actually use each particle as a thread, so we have a much finer grain of parallelism. So how can we make this better? Because if we leave it as this, we will have serial memory accesses to different positions, and it will be very inefficient. So one option is to use the shared memory, and we can use this block. So we introduce an internal vector for the entire field grid, and we load the values, synchronize threads, and then we will use this shared memory. A memory read from global memory is about 600 cycles. From this shared memory, it's down to 30 cycles. So we are 20 times faster already. It's not a big deal, but I mean, from the implementation point of view, but it's a big, big performance benefit. Another possibility is to use the restrict keyword. And you can see here that we have this black restricts everywhere. I don't know whether you've heard of this or are using it already. Restrict just tells the compiler that the pointers are not aliased. So they point to different parts of the memory. So you don't have to reload a vector if another vector is changing. But if we use the constant modifier, not only it will be a distinct memory area, it will be fetched into a local cache, so it will be much, much faster. And actually, using this alone can change dramatically the performance. So the move kernel went from 68 gigaflops up to 325 gigaflops. The other part is the density calculation, which is a very intensive thing again. And here we have many different approaches. This is basically a histogram. We want to collect the different charges from the particles onto the grid points. So you have to add these interpolated charges globally, but there's no global operation in the CUDA. You can use atomic add in the global memory, which is very costly, or we can use shared memory in two different ways. Either we use shared memory atomic operations and then global atomic adds, or we can use reduction in shared memory and then a global add. This is an illustration of the process. I think I'll skip this because I'm running out of time. The third optimization step was merging or fusing different kernels into one. And this has the advantage that we don't have to load and store data so many times. We just read it once and do more operations. So hopefully the operational intensity is increased. And this bottom figure shows the Nsight tool that you can use for another objective performance check. This is the so-called speed of light analysis. You can see this is one kernel, and this shows how much of the peak performance this kernel achieves. Okay, you can use it from the Nsight tool. So we are roughly, well, almost at 20% after the optimization. The last bit that I want to highlight is the Poisson solver. We didn't touch this for a while because on the CPU it was not really important, and actually 2 microseconds is all the time it requires. The problem is that when you copy the data back and forth, it will go up to 200 microseconds. So it's a very, very expensive operation. So we use now a GPU implementation, which is a hybrid merge of the cyclic reduction and parallel cyclic reduction, 3-diagonal solver. Reference is there, and actually the code is available on GitHub if you're interested. And now the time is about 14 microseconds. For the 2D case, we use the standard successive over-relaxation method, and we don't have too much problem with that. So this is a timeline of the optimized 1D simulation, you can see the fused kernels, one for electrons, one for ions, and then the Poisson solver, and they are quite evenly distributed in time. We also experimented with streams. I think I'll skip that, maybe too much for the end, because it didn't really work. It's very nice, but it didn't work. And that's the timeline. The idea was to overlap kernels, execute them concurrently, but the performance didn't improve as much as we expected. So this is basically the summary. With different steps, we started with roughly 50 seconds for a 100-cycle simulation, and now we are down to 5, which is a 10 times speed up on the GPU. So that's an objective measure of performance increase. And overall, we have 100 times speed up for a one-dimensional system. These are not important. So I'll jump to the conclusion. So after about a year of hard labor, the originally 15 times faster 1D simulation is now up to 100 times faster, which is a huge difference. So a 3-month simulation can be done in 1 day, which is a big difference. And also we have a performance increase, basically doubled performance for the 2-dimensional case, but we still have work to do in the 2-dimensional case. The particle movement, you can see, dominates the execution time. So hopefully we can improve that a little bit. Thank you very much.
Okay. Thank you, Zoltán. Time for questions.
Would the speed up be as good in 3 dimensions, or even better, or is there a bottleneck?
Good question. I would expect better. The more particles we have, the more efficient the GPU will be. We can see that already on the 2D case. So even in the 1D case, if we move from, let's say, 60,000 to 150,000, I would expect performance increase, because basically there's not enough work. There are too many stalls in the execution. So yes.
Other questions?
Wait. So how many particles? That was the question. In the 1D case, we have 60,000 electrons and ions. In the 2D case, we have 10 millions. And we hope that the 1D case will go up significantly.
Okay.
You were talking about the stream version. You didn't do it in full detail now, but what was interesting to me was that you were saying, like, yeah, the speed up was not that good as you were expecting the speed up to be. Is there a speed up at all? Because we have, I was finding that having 2 kernels executing simultaneously should not work at all, or speeding up at all.
Yeah, you were asking the streamed version,
yeah.
Right? There was speed up, yes. The best result was 5 seconds for this 100 cycle, and with the streamed version, we got down to roughly 12 seconds from the original 46. So we had considerable speed up, but the other was much better.
But you dropped it because of the complexity of the implementation.
Yes, it's more complex and it's not performing as well as the simple one.
Okay.
But we may come back to it in a later stage, in a more, maybe in the 2 or 3-dimensional version. So it's always difficult to judge, because the optimization is one particular instance of your program. And if you change something, either the size or the dimensions, maybe the not so good methods will work again.
Thank you.
So it's a constant experimentation, really.
Okay.
I think we better stop.
I have a question regarding the CPU version of the Poisson solver. Is it vectorized?
No.
No.
That was just normal loops,
Okay.
no vector
And
instructions.
was it possible to migrate the algorithm to GPU? Like GPU has completely different programming model. It says SPMD. And how did you implement it on GPU? I mean, was it straightforward to port the CPU?
The Poisson, or?
Yeah.
Well, I started to implement it, but by the time I got it working, I found the better version from NVIDIA. So I just used that.
Okay,
So it was straightforward. Just download it from internet.
cool.
Okay. Any further remarks? Okay, if there's no, let's thank Zoltán again.